In calculus, we are used to sequences naturally finding an answer. But in broader metric spaces, a sequence can look like it is honing in on a solution, only to arrive and find that no point exists at that location. To understand why this happens, we have to look at how we define the target. A convergent sequence is a series of points marching toward a specific existing destination within that space. But a Cauchy sequence is defined differently. Here, we only look at the points themselves. If the distance between the elements is shrinking and they keep packing tighter and tighter together, it is a Cauchy sequence. The sequence itself does not care if a destination point actually exists at the center of that cluster. This distinction brings us to the definition of completeness. A mathematical space is complete only if every single Cauchy sequence in that space hits a target that exists inside it. Think of the solid real number line compared to the rational numbers, where a sequence can aim for the square root of 2, but end up falling through a gap because that specific coordinate is missing. A complete space guarantees there are no hidden holes. This property is the requirement we need to prove that solutions exist when dealing with higher mathematics. To prove a metric space has no holes, we use a specific three-step blueprint described by mathematician Erwin Kreyszig. Step 1 is construction. You take an arbitrary Cauchy sequence and use its own properties to extract a candidate limit. You are mathematically building the suspected target. Step 2 is verification. You have to prove that this newly constructed limit actually belongs to the specific space you are testing. It must meet the formal criteria of that set. Step 3 is the convergence check. You have to show that the original Cauchy sequence actually reaches this new limit, specifically measured by the distance formula, or metric, defined for that space. Skipping any of these 3 steps renders a mathematical proof invalid. We will apply this sequence as we move into analyzing more complex spaces. Let's apply this blueprint to a tangible geometric space, n-dimensional Euclidean space, or Rn. We start by taking an arbitrary Cauchy sequence made up of multidimensional vectors. This shows how we break the problem down. Projecting these 2D vectors down, the coordinates on the x and y axes form Cauchy sequences of real numbers. Since the real number line is complete, each sequence reaches a real number. These provide the exact coordinates for our new target location. Assembling those limit coordinates completes step 1 of our blueprint. Since any finite vector of real numbers belongs to Rn, we clear step 2. Applying the standard Euclidean distance formula to the components satisfies step 3. Proving that complex spaces are complete often relies on this technique, breaking the elements down to utilize the foundational completeness of the real numbers. We can apply this exact logic to L infinity. This is the space of all bounded sequences. Here, every element of our Cauchy sequence is itself a full sequence of numbers. Visualizing this Cauchy sequence as a grid instead of algebra, we highlight one vertical column. This isolated column is a Cauchy sequence of real numbers that converges to a single limit number. Repeating this for each column forms a new horizontal row, our candidate limit sequence. Based on our blueprint, what exactly do we have to prove next for step 2 and step 3? For step 2, we must prove that this new limit sequence is bounded, so it belongs in L infinity. For step 3, we show that the supremum distance from our original sequence to this new limit goes to 0. Visualizing these algebraic indices geometrically prevents the notation from obscuring the underlying logic of the proof. Sometimes we can bypass the 3 steps entirely. If a space is a closed subspace of an already complete space, it is automatically complete. But let's look at the function space CAB, the set of all continuous functions on a closed interval. Under the maximum metric, distance is determined by the largest gap between curves. This metric forces uniform convergence, which guarantees that the limit function will remain continuous. Changing to an integral metric, distance is calculated by the area between curves. Here, a sequence of continuous functions ramps up, becoming progressively steeper each iteration. As the ramp steepens, the area between these shifting curves shrinks to 0, making it a Cauchy sequence. But look at the pointwise limit. The result is a step function with a sharp break. It is no longer continuous. Because the limit function does not belong to the space of continuous functions, the sequence fails step 2 of our blueprint. Completeness is not a property of a set of items alone. It is dependent on the specific metric applied to that set. Change the way you measure distance, and a complete space can develop holes. Completeness is the mathematical guarantee that a space does not have gaps where answers disappear. This checklist lays out exactly what we have proven. Rn, L-infinity, and continuous functions under the max metric are complete and airtight, but the rational numbers, polynomials, and continuous functions under the integral metric are incomplete. They have gaps. When you evaluate the boundaries of any new abstract space, you can rely on the structure of this three-step process. To see this process applied to Hilbert or Banach spaces, subscribe to the channel and let us know in the comments what theorem, chapter, or textbook we should explain next. Mastering these rigorous proofs provides the framework to guarantee physical solutions in applied fields like differential equations and quantum mechanics.